This is Algebra 2, Lesson 7.4, Evaluate Logarithms and Graph Logarithmic Functions. So first we really need to develop the idea of what is a logarithm. Logarithms allow you to find exponents. So if I have a problem that is 2 raised to the x power equals 6, it gives me the way to figure out that x. Log base b of y, that's how we read that. That's how it's written. And then this is our log form, and this is our exponential form. So those are exactly equivalent. So I wanted to start with log base b of y equals x and kind of show you how we get that. So this is my base of my log. It's also a base being raised to the exponent. So this is my base. My exponent is what the log is equal to. That's across the equal sign. And then it's going to equal that y. So that's b to the x power equals that y. Examples of where logarithms are used would be like a Richter scale or a pH scale. So you might remember when people talk about earthquakes, how they talk about like a 6.0 earthquake versus a 7.0. It's not just like one bigger, it's 10 times bigger. And that's because we're working with logarithms instead. So first, we're just going to practice rewriting an exponential form, just getting the mechanics of that. So remember, if it's log base 2, that means 2 is also my base. My exponent is what my log is equal to, so 2 to the 5th power equals 32. On the second one, 10 to the 0 power is 1. Sometimes people draw like a fancy cursive E through that to help you remember. I have a hard time. It doesn't look like an E to me, but it might help you remember. So 10 to the 0 power is 1. For C, I would have 9 raised to the 1st power is 9. And then for D, I would have 1/5 raised to the negative 2 power. So I've got to have that in parentheses. I need to raise the entire fraction is going to equal 25. So that's just some practice taking a logarithm and rewriting it in its exponential form. So these two things are exactly the same, except one of them, it's equal to the exponent, and the other one, it's written in this exponential form where you have an exponent to start with. So now we're going to go through and we're going to practice evaluating. So to evaluate, we're going to make them equal to x, and we're going to rewrite an exponential form. So first, we're going to set equal to x. 2, we're going to rewrite in exponential form. So let's go ahead and do those 2 steps. So we made it equal to x. Exponential form would be 3 to the x power equals 81. And now we're going to rewrite so that both sides have the same base. So I'm going to write get same base on both sides. So because I have 3 raised to a power, my base is 3 on the left. I want to make it so that I have a base that's 3 on the right as well. So I know that 3 to the 4th power equals 81. So I'm going to write 3 raised to the x power equals 3 raised to the 4th power. So now that I have the same base on both sides, I can make my exponents equal. So that's our last step, set exponents equal. And sometimes we'll have to solve, but this one we just get our answer right away, x equals 4. This is the way the work will have to be shown. You're going to have it equal to x. You're going to have to make it exponential form. You have to have this step right here. I don't care that you can look at this and say, oh, x needs to be 4. You need to show this step where we have the same base on both sides. That's going to be absolutely critical to some of the problem solving that we do later on. So we want to make sure that we're doing that. B, I am going to do the same steps. First, I'm going to make it equal to x and then rewrite an exponential form. 1/4 raised to the x power equals 256. And then I want to make it so that there's the same base on both sides. I'm thinking instead of 1/4, it would be better as a 4. Since the 4 is in the denominator, that would be a negative 1 power, and there's already an x there, so power to a power would be negative 1x. 256 is 4 to the 4th. And now I can make my exponents equal. Negative 1x equals 4. Divide by negative 1. X equals negative 4. So we'll go ahead and look at a couple more. Here's one with a decimal. Make it equal to x again. So 10 to raise to the x power equals 0.001. So let's think about what decimal place this is in. Tenths, hundredths, thousandths. Since it's in the thousandths place, I can write it as 1 over 10,000. That's what that means. Oh, sorry, thousandths, not 10,000ths. So we have too many zeros here. So let's make it 1 over 1,000. And now I need to think about how 1,000 is 10 to the third power, but it's in my denominator, so we're going to make it a negative third power. And so x is equal to -3. So I probably showed a little bit more work in here than I had to. I think this step is necessary. This step here, maybe you could have skipped that and gone directly to 10 to the -3rd. But in our notes, we're always trying to show like every single little detail so you don't wonder later on what we did or how we got something. For D, we're going to set it equal to x as well. Guess I got to turn my marker back on. And 64 raised to the x power equals 2. So on the right, I have 2 to the first. On the left, I'm going to have to make that 64 into a 2. So 2 to the 6th power, 2 raised to the 6th power is 64. So this will be 2 raised to the 6x power equals 2 to the first. So 6x equals 1. Divide by 6, x equals 1/6. So your first 7-4 worksheet will just be doing a bunch of these problems and getting a feel for how logarithms work. So the rest of this lesson is really going to be helping you for your next homework assignment. So common logs. So common logs are a special logarithm where we don't write down the base. So if we just write log base 10, or if we just write the word log, it's understood to be base 10. Just like when we write a square root, it's understood that there's a little 2 here. When I write log by itself, it's understood that there's a 10. We call it the common log because our number system is base 10. So it's the one that makes the most sense for us. So when you look at things like common things like Richter scales, remember how we talked about how one earthquake was 10 times bigger than the other? That's because that's going to be at a base 10. So we also have natural logs. So because e was such an important number looking at continuous growth, we need a log base e to undo that. Logarithms and exponents are going to undo each other. There are inverses. So instead of writing log base e every single time, we just write natural log, which is ln. So the L stands for log, the N stands for natural. So it is not an IN, it's an ln. So ln is natural log. So for our third example, you're going to use your calculator to evaluate the logarithm. Sometimes you put the number in and then the word log. Sometimes you press the log button and then the number. So what I've done is I've given you the answers to tons of decimal places. So as you're trying to do this on your calculator, you're able to really check your answer and make sure you're doing it correctly. If I only gave you 2 decimal places, you might worry that you had done something wrong. So make sure that you pause this video and try using your calculator. Example 4, we are skipping on your notes. Inverse functions. So we know that logs and exponential functions are inverses because I've told you that. But what that does is it gives us some properties. So let's think about what g of f of x means. That means I would take all of f and I would substitute it inside g where that x was. So that would give me log base b, not of x, but of this whole function, b to the x power. And I know that if I have inverses, they cancel each other out and I'm left with x. Now, if we worked kind of the reverse method on this, I could take this log base b of x, and I'm going to substitute it into my other function, into f, where my x is. So now I'm putting g inside f, and then I would get b raised to the log base b of x power equals x. So the inverse functions, those definitions are going to give us these log properties. So these are log properties we can use. And so the way that would look, I'm just going to give you a couple quick examples here with just numbers really fast. If I had log base 4 of 4 to the x power, that's just going to equal x. If I have 7 raised to the log base 7 of, let's say, 9x, those 7s match, that's just going to equal 9x. So that is how those properties work. But those are log properties that we can use, and they come from this idea of inverse functions. So now we're going to look at simplifying, and we're going to use the log properties here. You could also solve these by making equal to x, but we're going to practice with those log properties. So here I need to remember that natural log is base e. And if you have to, write it in. And so because my bases match, we're just left with 9 again. You know, we always talk about canceling it out, kind of in quotes. It's not really proper math to say that, but that makes sense to us. On this one, in order to get that same canceling effect, I'd have to have this be a 3. So I'm going to write this as log base 3 of 3 to the 3x power, because 3 to the third is 27. And then again, I have a base 3, and then this is a base being raised to a power, so I just get 3x. I'm left with that exponent that I had, the 3x. So that's how we can use those log properties. So these log properties are not going to be used on the first worksheet that we're doing. Again, we're doing extra stuff that you'll do the day after. So find the inverse. So we're going to practice, because in chapter 6 we learned about inverses. So now we're going to kind of practice that in different chapters. So to find the inverse, remember first we swap our x and y. And then we're going to solve for y. And then our last step is to write it with our function notation. So I'm going to go ahead and switch my x and y around. And then because I can't get that exponent, but I do have this really awesome log property, if I want to be able to get to that exponent and make the other part cancel out, I am going to take a log base 8 on both sides. And there's other ways of doing this. This is just the way that I think will make more sense to you guys. So that means on the right now, because I have a base 8 and I have this 8 raised to a power, that's just going to be y. And so now I have y by itself and my function notation. And done. So this is just trying to practice inverses now in this chapter 2. This isn't a terribly big skill that's super important, but I think it's good to kind of link what we're doing now with logarithms to what we learned in the last unit. On B, I want to switch my x and y as well. And now on this one, the variable that I need is inside my logarithm. So instead, like on this one, I knew I had 8 raised to a power, so I did log base 8. This one I have natural log of something. Natural log is base e, so I'm going to raise both sides. I'm going to take both sides and raise them as a power of e. And now, because I have e and I have a natural log base e on the right, I'm left with y minus 4. And then I'm going to add 4 on both sides. We're really going to work on this raising both sides as an exponent or taking a log on both sides. That's a skill we're going to use more in 7-6. So if you're struggling with it right now, it's okay. The way the book teaches this, which you might want to look at instead if you want a different method, is just changing back and forth between log form and exponential form. But I have found that even though we're jumping the gun by teaching it this way, it makes it easier in the long run. So now I want to look at graphs for exponential functions. So here we're showing exponential and log functions. So here we are showing this exponential function. It has exponential growth like we've looked at. So it makes sense that the logarithmic function would be reflected over that line y equals x. And then here is one that is a decay function. And then if I reflect over that line y equals x, I would get my inverse or my logarithmic function. So this is just kind of to notice how those two, how those look and how those match up. And just kind of see the shape of a logarithmic function before we actually try graphing. And we are going to practice on a few of these. We're trying to always give you guys a visual And I like this idea of connecting a function with what its inverse looks like. So in order to graph, logarithms are really weird. I always change them into the exponential form. So I'm going to rewrite this as 2 to the y power. Remember, my exponent is across the equal sign of x. So 2 raised to the y power equals x. And when I make my table, notice my x and y are swapped around. So that should be making you think inverses. And because I am raising 2 to the y power, it makes sense to let y be -2, -1, 0, 1, 2. And when I'm graphing an exponential function, those are usually my x values. So again, when I have an inverse, I am swapping my x's and y's. That's exactly what's happening here. So now when I fill out this table, 2 to the -2 power, this will be 1/4, 1/2, 1, 2, and 4. And I got to tell you, these are tricky to graph because we're so used to graphing exponential. So if x is 1/4, y is -2. When x is 1/2, y is -1. When x is 1, y is 0. When x is 2, y is 1. 4 is 2. I'm going to add one more number here because I can. If my y is 3, 2 to the third power is 8. So 8 for x, 3 for y. So my function looks like this. So again, think about how that exponential function would look and how we have reflected that over that line y equals x. So now I want to go ahead and think about my domain and range just to practice with that. So before, our domain for our exponential functions was all real numbers. But now our range is going to be all real numbers. So when we have inverses, not only are we swapping our x's and y's, we're also swapping our domains and ranges. Before, I had my graph entirely above the x-axis for my range. My range was y greater than 0. Now my domain is going to be x greater than 0 because I don't have anything over here where x is negative. So I have an asymptote at x equals 0. I'm just going to squeeze that in the middle. Actually, I should have done one more line. Maybe I could move it. Nope, it's not going to let me move it. All right, so our asymptote is this vertical line now. Now it will let me move it. How weird. I didn't change anything else. So now my asymptote would be this vertical line instead of a horizontal one. So before I had an asymptote at y equals 0, now I have an asymptote at x equals 0. So again, we are just swapping all of our x's and y's here. We'll look at one now that's a fraction instead. So when I write this as exponential form, I will have 2/3 to the y power is equal to x. And again, because I'm doing a logarithmic function, I'm going to actually use that -2, -1, 0, 1, 2. Those are going to be my y's. And then let's see if I take that and I raise it to the -2 power. I'm flipping and squaring, so 9/4, 3/2, 1 2/3, and 4/9. So we'll go ahead and graph. Let's see, x is 9/4. That's a little bit more than 2, 2 and 1/4, and then down 2. 1.5, down 1. When x is 1, y is 0. When x is 2/3, y is 1. And then I think I'm just going to stop that right there. So this one's going the other direction from our last one because we have a decay. Our domain and range is still the same though. And then we do want to look at graphing one where we have some shifting going on. Since it says x minus 2, that means I would shift it a positive 2 units in the x direction, so 2 right. So it's always, remember, opposite sign, same sign. Plus 4 is like my y-intercept, so it's going to go up 4. So I am not going to worry about the shifting right away. I'm going to make a table for y equals the log base 3 of x, and then I'm going to shift that table. And I do need to change this to exponential form. This would be 3 to the raised to the y power equals x. And then for my table, I'll have -2, -1, 0, 1, and 2. So let's fill in our x values. And then we'll go ahead and graph. This first one's too small. I'll start with x is 1/3, y is -1. It is just not wanting to let me move it. Okay, and then I'm going to take each of these points and move them up 2 and 4 to the right. So I think I'm going to start with this one, up 2. Oh, wait a minute, up 4 and then 2 to the right. 1, 2, 3, 4, 2. It's a good thing I stopped. 1, 2, 3, 4, 2. 1, 2, 3, 4, 2. My asymptote is going to move 2 units to the right as well. So instead of an asymptote at x equals 0, we're going to have an asymptote at x equals 2. And I didn't move this first point because it was a fraction, but I don't really need it on the graph to be able to tell where my graph is. So my graph is over here. So let's think about domain and range again on this one because it's more interesting. My asymptote is at x equals 2. And so my domain is x greater than 2. And my range is still all real numbers. And this is it for our 7-4 notes.